Okay, so now we're going to, where'd my lights go? Now we're going to go through the forces. So I said that you would need 4 forces, right? So what were the ones we were going to go over? Let's see. We talked a little bit about this. We'll be doing a lot of this. But here we go. Gravitational, normal, friction, and tension. So let's do the first one. Let's do weight. The first force we got to think about here. Now I'm going to do a definition a little simpler than what you'll see in the book, and I'll explain the difference. But let's just go with 99.9% of the time what you mean by the weight, okay? The force of gravity on all objects near the Earth at all times. It doesn't turn on and off. And there's something that confused people for 2,000 years. Gravity seems to pull it down, but now it's stopped. Where'd it go? Where'd the gravity go? Oh, there it is. Oh, now it's stopped again. Right? It looks like gravity turns on and off, depending on if something is supported or not. But it doesn't. It's always there. Right? It's always there. And do you feel gravity? Do you feel your weight? No, you don't. So that's part of the reason it's hard to know. So the symbol we'll use for weight is a lowercase w vector, right? And the formula for weight is it's the mass times the gravitational acceleration. So this is a constant of the universe, or a constant of being near the Earth, where g is the gravitational acceleration, its magnitude. Remember, those are the magnitude bars. It equals 9.8 meters per second squared. It's really 9.81, but we don't need the 1. Just use 9.8. It varies as you move around. Okay? And the direction is down. There you go. The direction is down. What does down mean? Towards the center of the Earth. Toward the center of the Earth. If you want to get technical, the Earth is spherical. I don't know, you might read differently on the internet or from the president or something, but the Earth is a sphere. The only other weird thing about weight is if I were to say I want to do a vector diagram of weight, well, where do I draw the vector? Remember, we used to worry about when we talked about position, velocity, acceleration, we kind of said position you have to draw from the origin because you're usually drawing an XY coordinate system that's actually space. And position is space, so it matters where your position vector goes. Velocity and acceleration vectors is sort of an artistic choice. All right? If something is moving with a velocity, put the vector on it. It looks nicer. Weight is not really an artistic choice. Technically, it acts at the center of mass. Okay? It effectively acts at the center of mass, which I'll abbreviate COM. And later in the class, we'll actually calculate where the center of mass is, but here's a preview. It's in the center. Okay, so if it's a square or a rectangle, it's in the middle, right? So if you're going to try to draw it and make it sort of physically accurate, you would want to draw your weight vector right there. And we'll get more into drawing and free body diagrams in a minute. But that is where it acts, okay? Let's see, so that's weight. Now, what's confusing is, if you read the book, and they're correct, is that you can also define weight as the normal force, or as the reading on a scale, right? So you could say mg is the gravitational force pushing you down. The weight is what pushes back up on you when you stand on something. So take a spring scale, you don't know how that works, but just take one and stand on it, and that's your weight. And then you get into weird things about how that changes when you accelerate, and that's your apparent weight, not your true weight, blah, blah, blah. Let's not worry about that. For what we're going to do for most of the time, weight is just mg, okay? And it's so standard it's just mg. A lot of times when I do a drawing, I'll just put mg like this. I'll try to remember to put w, but most people just write mg, okay? But there are weird cases when things are accelerating where the definition of weight gets a little funky, but don't worry about it, okay? So we got weight, we got g, we got the center of mass bullet here. What else do we need to say? Okay, so what is mass? We haven't talked about mass. Mass is a little weird and confusing. Right now I'm just going to tell you the important thing is that mass is the quantity of matter that something has, right? So this has a small mass. This has a bigger mass. It's how many electrons and nucleons are in it, okay? It's an intrinsic property of something. How much mass it is how much mass it is. It doesn't matter where you go, okay? Technically, weight is extrinsic. Or I don't know if extrinsic is the right word. Weight depends on local gravity. So the main thing is not to use those interchangeably. Now, you're definitely not going to use them interchangeably because mass is a scalar. It has nothing to do with weight or force or gravity. It's just a property of something, and it's a scalar. It's just the mass. It's how much there is. And weight is how gravity acts on that mass. That's a vector pointing to the center of the Earth. And weight varies because really this 9.8 is sort of the average, near. If you go up high enough, it goes down. Little g gets smaller when you get really high up in the air. We'll calculate that later. As you move across the Earth, little g gets smaller because the amount of mass right under you matters, right? So this is how they find oil, right? You drive the ship around and measure g fluctuating. I just had a guy in my office describing this in excruciating detail a few weeks ago. How they have very sensitive devices that measure g with a bunch of gyroscopes spinning around, and they fly it or they do it a ship or an airplane, and when they see low g, they know there's oil there. Because oil is less dense than rocks. So the variation of G is important and is mostly measured to find oil, or sometimes in demonstrations. Let's see. Right, and then the last thing about weight, I won't write it down, it's not really important, it's just for fun, is that you can't feel your weight. Right? We were born, evolved, and grew up feeling mg, so we don't really sense it. When you think you feel your weight, you're feeling something pushing up on you. Right? If I stand here and I feel like I can feel my weight, I really feel the floor applying a normal force, which is our next force. I can't really inherently feel my weight. If I jump, or if I'm in free fall for some reason, some ride at an amusement park, I feel nothing. But mg is still acting on me. Right? If I'm falling on one of those, what's the thing where you're on a big rubber band and you hope it doesn't break? If I'm bungee jumping, I'm weightless for a minute. But weightless is a misnomer, right? I still have a weight force, I just don't feel it.